Now life's exactly how it used to be because we have train X, train Y, and test X, test Y exactly how we want it. And this is actually the crazy huge file, okay? So we have our whole implementation up above, and we still have this from scikit-learn.linear model, import linear regression. Let's just basically copy this code because it's going to be really the exact same thing. So here we have this, and we can do line. We'll change line here to be, we'll say California or population line actually. So pop line, we're trying to predict the population, and we'll fit that with what data? Well, we want to give that train X. Okay, there's our matrix right there. We want the Y values to be train Y, and we'll show the intercept as well as the coefficients. Okay, that one's not going to change at all. All right, the input contains not a number, infinity, or value too large for float 64. Oh yeah, we're going to see sorts of errors like this all the time. Now, I purposely led you to this error to show that you've got to check your data sets, and it's a really bad assumption to assume that everything's totally fine. Input contains not a number, okay, is really the problem here, which basically just means we have missing data, okay? And this goes into the data cleaning part, which is because we have stuff in here that just doesn't exist. Okay, everything here, every row you see, actually it has the values here, except it turns out that there is values that are missing. And we found out that later. Okay, so how would we fix this? Well, then we could go into more data cleaning later for sure, except for now, we can do what's honestly just really easy. And to be honest, what people do most of the time is just df is equal to df.drop_na. Okay, and that is most easily shown what it does by giving you the output, which is now we have 20,433 rows and 14 columns. Okay, so we removed about 300 values here, 300 rows of information, because we just found data in here that didn't exist. Okay, it says some here, it says NaN, NaN, they're mixed in here. There's missing data. We say, hey, just set this data frame equal to the drop NA. We remove that, and so we only keep the stuff that has we only keep rows that have a full set of information. And now we aren't going to have that problem. We do need to run everything here again, but that's not an issue. And so we do that, and then we get our model here, which is something pretty complicated. It's outputting a lot of different coefficients because we have a lot of different coefficients. We have, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, which makes sense. It's 13 variables that we're predicting plus one intercept term right here. And now we can check the MSE or the error of our model. As with before, we can get the training and the testing error very easily. If we have the pop line here, which is our model, well, we can just get the prediction of that. So we do predict with train X, that'll get our training predictions, which it actually used already to train the model. So that's that. And then we have train Y is our real answers here. And so we can get the MSE with our same function as above right here. It is a huge, huge value, okay? There is so much error here. Except think about what this actually is. This is the mean squared error. If we're predicting the population and we're off, okay, so here, look at our population. Maybe, for example, we're off by, 300 people. That's honestly not that bad. Like that could be pretty good for some of these answers. If we were trying to guess 2,400 and we actually got like 2,100, that's not that bad of a guess, to be honest. And so what is 300 squared? Well, 300 squared is a really, really big value, okay? If I was to do 300 squared, that's 90,000, okay? So obviously this number is bigger than that, 193,000, except what this is really telling us is that the MSE is not giving us an answer that's telling us how good our model is. It's a function that we'll look at a lot that is used to train the model, except to actually look at how good it is. Honestly, the MSE isn't great here. And so I'm just going to kind of slip this in here, and we'll look later a lot about how to actually interpret models and know that they're good. But right now, I want to show you that there's this thing called score. Okay, if I do popline.score, and what I pass it is train X and then train y. And so this gave us a value of 0.85, which, although I'm not really telling you what it is a value between 0 and 1. And if you want to look up what this is, it's called r squared from scikit-learn's model. It's just a way of measuring a linear regression model between 0 and 1, and the closer to 1 is ideal. And it basically says, it's a little bit more complicated than this, but it basically says how good your model is. And if it was a 1, then it's really, really good. And if it's 0, then it's really, really bad. Okay, so 0.85, clearly it's on the better end. It's actually on, the better end of the better end. It's not super, super top, but it's a pretty good model. And so the MSE, this is great, and we'll look at it a ton for training the model, except I'm giving some intuition to show this is not a function that we always use to tell people, hey, your model's pretty good. No, you might try to minimize this thing, but this is what we actually might use to tell people how good our model is in the business, or just yourself understanding what's going on. So that brings us to the end of this project, and what's crazy is we still aren't done with linear regression. We're going to go into the really, really machine learning point of it now. All of this stuff, it's really important to understand all these concepts from a statistics point of view, but here we are going to go full into machine learning with taking the derivatives of things and doing the machine learning point of view.